Now I'm going to go over some more specific details of pressure and airflow. So we're going to look at the stack effect and how do you counteract that in a building. We'll look at some other things that can impact pressure differences within and outside of a building. And then we'll look briefly at what a blower door does as well. This is a reminder from the previous presentation. Remember that an air barrier or a pressure barrier limits airflow, and that a thermal boundary or thermal barrier or the envelope that limits heat flow. Okay, we want to have a good, efficient building. We'll have continuous thermal and air boundary over the entire building envelope. Okay, so there should be continuous and in contact and everywhere. You don't want any gaps in the air boundary. You don't want any gaps in the thermal boundary. Very important to have that continuous as possible. And if we see areas where it's not continuous, then we want to fix that. Remember that for every cubic foot per minute that leaves the building, an equal number of cubic feet per minute comes in. And for every cubic foot per minute that comes in through, say, ventilation, an equal amount of cubic feet is going to leave. Okay, so it's always balancing out. It's always a give and take. Remember that airflow, once you have these pressure differences, that air is going to find the path of least resistance. If there's a wide open window, it's going to go out the window. If it's a pretty tight building, it's going to find a little crack and find the sort of weak point in the building structure. And remember the difference between ventilation, exfiltration, and infiltration. Infiltration and exfiltration are leaking out and in, and then ventilation is mechanical, purposeful, I guess you could say, infiltration. Okay, so we've talked about how pressure impacts air movement, and now we're going to look at some specific examples. We're going to focus really today, we're going to ignore the wind. It's really not a big part of your consideration. We're going to look at the stack effect and the effects of combustion, and also the effects of exhaust fans and how that changes the pressure regime in a building and how that impacts air movement. So this is really, really, really important. So jot this down. When you force air toward an area, you increase the pressure in that area. Okay? Decrease the pressure from that area. Okay? And I'm going to give you a quick example here. I'm going to draw this with my mouse, so excuse me. But if I have a wall, right, and the floor, and I have a little space heater in the corner, right? So what's happening with this space heater is this air is going to rise up through right? So what's happening is the air around the space heater, here and here and here, is going to rise up. So what that does is that ends up lowering the pressure right next to the space heater. And when you pressure, it's lower with respect to areas around it. So that air is going to actually be pulled in toward that area of low pressure. Okay, so that little low pressure zone is created by that air moving up. And again, when you move air from an area, you decrease the pressure. And so at the same time, where this air is going is going to end up being a relatively high pressure zone, because when you force air towards an area, you increase the pressure. Okay, so that's going to come in handy, especially when we talk about the stack effect and some other things in this session. Okay. So remember that. So remember, when warm air, when you force air toward an area, it increases the pressure. When you remove air from an area, it decreases the pressure. Okay, so let's look at the stack effect. You definitely want to jot down stack effect. This is really, really common in residential and commercial buildings. And so what causes the stack effect is when you have warm air in the winter rising up through the building, right? So you have something generating heat, and all that heat, a lot of it is moving up because of convection. All right, so what happens is that air is being pushed up through convection, and then that in turn, you end up pushing air toward the top of the building here, and you increase the pressure. Remember, when you move air toward an area, you increase the pressure. And at the same time, since the air is moving away from the lower part of the house or lower part of the building, you create negative pressure there, or you lower the pressure. Okay? So once the stack effect gets going, the heater kicks on, it's on for a little bit. What happens is you end up with this high pressure zone toward the top and a low pressure zone toward the bottom with respect to the outside of the building. Okay? And so if you have high pressure here with respect to outside, what's going to happen is that air is going to push out. And so that's where a lot of this air is going to leak out toward the top of the building, high pressure up here. And then the opposite happens toward the bottom. You have lower pressure here, higher pressure outside. And so what's going to happen is that air is actually pushing in toward the bottom. And so you have these two very distinct pressure zones when the stack effect has established itself. Then you have the high pressure at the top with respect to the outside, and so that air is going to be pushing out at the top. Low pressure toward the bottom with respect to the outside, again, because the air is moving away, and that air is going to come in to replace it. Okay? So this is really important. And it can be a little bit confusing because it's kind of like the air starts moving and that causes pressure and that causes more air to move. So you have to sort of think of this step by step. So let's go back to the one, the air rises. So that creates a high pressure zone up high and a low pressure zone down low. And that consequently is pushing air out toward the top, away from the top, and pulling air in from the bottom. Okay? And so what you'll have then, this is really common in situations like this with the stack effect, top, if it's not tightly sealed, is going to leak out at the top, especially toward the top. And some cold air is going to be leaking in the bottom. Okay? Because remember, the air is just flowing from higher to lower pressure. And so it's higher pressure outside, it's flowing in. It's higher pressure inside up here, it's flowing out. And so that's why it's really important to have the very top of the building sealed and the very bottom. If you do anything in a house for air sealing or a building, you want to seal anything up high, like the fan joist, the top plate, the ceiling joist, all that stuff. Excuse me, the rim joist, and then at the base you want to seal all that too. So the band joist that wraps around the bottom plate and everything like that. Okay, so that's where your most significant leakage is going to be because of the stack effect, toward the bottom and toward the top. And then somewhere in between where those two meet, there's this neutral pressure plane. Okay, so this is a it's sort of like goes from the two extremes, right? So the highest pressure is up high, the lowest pressure is down low, and as you get closer, it's going to increase pressure, increase, and then it's going to be neutral, and then it's going to be positive, right? So it's this sort of continuum, okay? And so where you have the highest pressure is where you're going to have the most leakage, where you have the lowest pressure is where you're going to have the most leakage. This is the video, so make sure you watch this video that's posted in the weeks. This is a really cool picture of actually a stack effect in action. And so you can see this is like a 4-story building here. Looks like it's the winter time. We got some snow on the ground, and it looks like they're doing some kind of construction here. And so this is covered with a tarp. And you should, if you look carefully, you should be able to see a positive, negative pressure, and the neutral pressure plane. So go ahead and press pause and see if you can find it. So you notice at the top it's puffed out. Let's get rid of these arrows. See how it's puffed out up top? That's that air pushing out at the top. So that is your high pressure zone. And you can see it's being sucked in toward the bottom, right? So that's your negative pressure. That's your low pressure zone. And so the air is trying to pull in low and trying to push out up high. And somewhere in between, it's hard to tell. Maybe it's right around here. Maybe it's up here. Is your neutral pressure plane. And that's where there's really no real air leakage at the neutral pressure plane because there's no pressure difference. And so as you move further away from the neutral pressure plane, if you move up, the positive pressure increases, and so there's actually more, the higher you go up, there's more pressure, right? And at the bottom, it's the opposite. The further you go down away from the neutral pressure plane, the more negative that pressure is relative to the outside, okay? And so some implications of this are, number one, the further you go away from the neutral pressure plane, it's going to increase pressure up high and decrease down low, right? So the further you go away physically, it's going to increase and decrease. And the higher the delta P, the more air will leak, all else being equal, okay? So that means the further you get away from the neutral pressure plane, you're going to get more leakage, right? And then the further you go down away from it, you're going to get more leakage in. So around the neutral pressure plane, air sealing, not quite as important because there's really just not a big pressure difference there. So you're not going to get much leakage at all, if any. And so at the top, at the very top, that's where you're going to have your biggest positive pressure. And so that's where you really need to seal at the very top of the building because air is going to leak out there. And then at the bottom, you're going to have a very negative, which means air is pulling in. And so you definitely need to seal toward the bottom as well. Okay? So that's the stack effect in a nutshell. You have these high pressure zones up high, low pressure zones down low, and the air is being pulled in down low and pushed out up high. And then in between you have this neutral pressure plane. And it's all about air movement and how that causes pressure changes. So it doesn't matter what you're doing. If you're moving air away from an area, it's going to reduce the pressure. So if you think about what happens with a furnace, like we have here on the left, so a furnace needs oxygen to burn, whatever it is. Let's say it's a natural gas furnace. So you need oxygen. So where does it get its oxygen? Most of the oxygen comes from around the furnace. Now there are exceptions to this. We can talk about that later. But let's say that it's drawing air from in the building and it's actually pushing it out the flue. Okay, so what you're actually doing is taking air from inside and pushing it out. And so what does that do? Remember, you're removing air from inside the building, so that's going to drop the pressure. So when you're running a furnace and you're pulling air from inside and dumping it outside, you're actually depressurizing the whole building. And that creates this negative pressure. And what happens with negative pressure? Now your whole building is depressurized, at least a little bit. And so now you have a low pressure zone here with respect to outside. So where's the airflow going to be? It's going to come from the outside where there's a higher pressure. Okay. So to sort of wrap it up, we'll go back to the beginning, right? So when you start a furnace, you're pulling oxygenated air from inside and you're dumping it outside. When you do that, you depressurize, you move air away, so you create this low pressure zone. So you depressurize the whole house or whole building, and then that's actually going to pull cold air in from the outside. And again, there's ways to go around this through direct combustion, but we'll talk about that later. Same thing if you have an exhaust fan. So if you have a bathroom exhaust, a kitchen exhaust, or a laundry machine that's exhausting air outside. When you pull that air outside, guess what? Same thing. You're going to depressurize the house, which depressurizes the whole building, and that's going to force air to come in from outside the building. So think about a real cold winter day and you're running the bathroom exhaust fan. Maybe you're also running the kitchen exhaust fan. Maybe you're also doing laundry, right? Now you're exhausting air here, exhausting air here, exhausting air here. For every cubic foot per minute that goes out of the building, it's actually drawing in another cubic foot per minute. And it's drawing air in through the depressurization that's happening. Okay, so again, air moves because of pressure differences. That's it. That's the whole game. So if you're moving air, you're causing a pressure difference, which then makes more air move. Okay, so anytime you exhaust air out of a building, you're going to replace that with outside air, right? And so if it's cold outside, you have to heat it. If it's warm outside, like a hot summer day, then you're going to have to cool it down. So that's why exhaust fans can be a big energy user, not because of the fan, but because of the air that comes in because of the exhaust. And similar things happening within a building. So if you have, say, this is obviously an oversimplified, but if you have a supply fan here and a return fan here, so this air is being forced over here, it's being pulled from here, okay? And so what's going to happen is you're going to have a negative pressure zone here and a positive pressure zone here. And that's going to cause air to leak out from this room and leak in to this room. Okay, so you can have these pressure changes within a building as well. And this is a piece of equipment called a blower door, where we put this on an outside doorway, we seal it up, maybe we'll get a chance to mess around with it this semester. But you actually, there's a big fan here, and you blow air out. And so what that does is that depressurizes the building. Now you can flip it around and pressurize it. It's much less common, but usually you're depressurizing the building. And so what does that do? That depressurizes, which forces air to come in from outside. And so what you do with a blower door is you use it as an assessment tool to see how leaky the building is and also to see where the leaks are. So I can depressurize this building, and what's going to happen is it's going to force air to come in all these little cracks and crevices, all these indirect spots, and then I can use an infrared camera to pick up on those leaky spots. And you can also use a smoke pencil if you want. And this is just a picture of a blower door and a front door. See, there's a big fan, and this fan will blow out, and it'll depressurize the building. And so, to summarize, remember that when you move air away from somewhere, it lowers the pressure. When you force air toward an area, it increases the pressure. Okay, and then once you do that, then that forces air to move subsequently. So after you change the pressure, then air is going to move to replace that, right? So it's always going to go from the higher pressure areas to the lower pressure areas. Remember, it's kind of like this multi-step process for the stack effect in ventilation and furnace exhaust. It's all very similar. Number one, you have air movement, right? So with the stack effect, you have air that's moving from the bottom toward the top of the building, okay? And that causes a pressure change. So up high, air is forced into it, so that increases the pressure. Down low, air is being moved away from it, and so that decreases the pressure. And then what happens is air comes in to replace that low pressure area, and it's being forced out of the high pressure area. And same thing with ventilation and furnace exhaust, right? So you move air away from the building, you're depressurizing the building, which forces the air to come in. Remember that for every cubic foot per minute out, problem is that air has to be heated or cooled to make it comfortable, sometimes dehumidified, which we'll talk about later. And so that there's an energy penalty for that. And then finally, we can use a blower door to force depressurization and actually do some analysis of a building. Okay, so now you have hopefully have a good sense of what the stack effect is and how you can counteract it in a building. Remember, you counteract it by sealing the top and the bottom. And you've learned about other ways that pressure differences can occur within and outside of a building, and then also how we use a blower door and what that does in terms of pressure.